Okay, well, I'm attempting to set a record for all-time futility here. I think this is the 4th time I've done this answer key for the AP exam type questions. Anyway, I've had everything possible go wrong. I've run out of tape. I've had phone calls in the middle of it. I've lost a page while I was working with it. Here we go. From the top. The maximum value of this function. This is just a straight up square root function that's been flipped around and stretched, flipped both in the x direction if you factor out the negative and in the y direction from that negative. So you wind up not looking for when x gives you the maximum value, but what the actual maximum value is. Be careful, this is a common theme in these review problems. So the highest value of this function is just going to be 0. Okay, it is not 2. This function here is a 4th degree. Okay, it is going to have right-hand and left-hand behavior that goes in the same direction. If you take the first and second derivative, you'll see that there are potentially 3 zeros at 0 and then plus and minus radical 2. And then the second derivative gives you 2 inflection points at plus and minus 2/3. So from all this, and the fact that that lead coefficient is positive, we know that it's got to have 2 concave up sections and 1 concave down. It's got to be 2 relative minima and 1 maxima. Alright? For 3, we already have figured out that it's got 2 inflection points, so we kind of get a 2 for there. 4, straight up L'Hopital's rule. Alright? It's a 0 over 0 indeterminate form. Smack it with that derivative stick both ways, up and down. Don't do the quotient rule. Individually take the derivative of the top and the bottom, and you'll see when you get to this stage the h is gone from the denominator. You no longer have division by 0. You've got 1 to the 5th, which is 6 then, over 1, which is 6. Alright? Here you've got pretty much just a restatement of the mean value theorem. If you've got some point A at which the function is 0 and some point B where the function is 0, no matter what crazy stuff it does, you can imagine bringing down a tangent line. It's going to be 0 at some point. That's really all this is saying. There's some number that when you take the derivative at that point, it's going to give you the value of 0, which would be your secant line. Total number of relative maximum minimum points. This was one where as I was going through it, I misread this at first. I didn't see that it was the derivative, so I started to think about the graph of that. But it did say it's the derivative, so here when you've got your potential zeros for maximum and minimum points, it's really all about the sign change. There's no way that when I do a test point on either side of that, with the squaring it'll change sign. It's always going to be positive. Same thing here. It's an even power, so there'll be no sign change for these two. But at 0, if I try a little bit below, I'll get negative. If a little bit above, I'll get positive, and there is a sign change in the derivative, so we know there's 1 relative max or minimum point at 0. Okay? In 7, I believe that's supposed to say a conical reservoir, so I'll check and see if that's a typo on my part. I apologize. I'd have to throw that one out. But you can kind of assume that if it has the lowest point, I guess, that it's conical. But at any rate, the ratio is 2 to 1, so that allows us to make a substitution with R and H. And I can then, when I have my volume formula, which you should know, again, maybe it wasn't fair to assume that you would have these memorized, but you make a substitution, it's a related rate, the snapshot depth is 8, so that means the radius is 4. You fill everything in carefully, and I got negative 8 pi because it was dropping. They're telling you it's dropping, so you just go with the positive 8 pi. Alright, number 8, another L'Hopital's rule, 0 over 0 form. When you take the derivative of the top and the bottom, just be careful. You wind up getting 0 over 1, and that goes to 0, so that's pretty straightforward. Number 9, a relative minimum value is, so we're trying to find the minimum value of the function. We take the derivative to find where that happens, and the minimum value happens when x is equal to 1. But don't choose 1. Be careful, alright? Nearly got fooled on that again. it is when e to the 1 over 1 is the minimum value, and that is e. So the actual value is e when x equals 1. Number 10, same type of thing. They're looking for the largest area, okay? Not when that happens, what your x value is, but what the actual area is. So sketch this function. It's pretty much like a bell curve in the sense that when x is 0, you get your maximum value of 1, and then it decays on either side symmetrically because of the x squared. So hopefully you can sketch that sort of thing out. Then that point is going to be x comma and then e to the minus x squared. You write an equation for the area, you take the derivative, you solve it for 0, after factoring out, and you get radical 2 over 2 is the x value, but when you sub that in, you get the actual area as radical 2 over e, square root of 2 over e. Number 11, this is a good old-fashioned conic section. Don't do that too much anymore. But the way you look at these is let the minus sign be 0 and x is going to be plus or minus 2. This is the part that we're interested in because it's the point 6 comma 0. So a sketch of that is helpful. You again write this sort of Pythagorean identity. For the distance, we take the derivative. Anytime we're taking the derivative with the square root using the chain rule, that gets to go in the denominator. To find a 0, we only care about the numerator, which makes it much easier. It solves fairly quickly out to be x equals 3, and that's our answer. Number 12, I did get fooled on this one. I took the bait, hook, line, and sinker. They're looking for the sum of the squares where it's a minimum. I wrote my little equation about the sum of the squares being 200. I made my substitution. I did the derivative. I solved it expertly, and I got 10. But finding 10 for both of these, that's actually a maximum value. So that is the absolute wrongest of the wrong. This is the only one. There's no minimum value. All right, it's only a maximum value. 13, we've got two cars traveling. I've just sketched out this way. They're perpendicular, so it kind of takes the north, south, east, west confusion out of it. But one is at the intersection heading away at 40 miles per hour. The other one is starting at 90 miles away at noon, is heading to the intersection. When you write your Pythagorean identity and solve for it, you wind up subtracting, because this is heading towards the intersection while the other is heading away. When you do that, you get negative 200 over 50 gives you negative 4. Got to be careful with that one. If they were heading away, you'd wind up, I think, with like something like 68. In 14, taking this above problem, you again write a sort of Pythagorean equation for the distance. Now when you take the derivative, again you've got a numerator and a denominator with the minus 1/2. You can ignore that and only solve the numerator. Being careful to distribute. I nearly made a mistake here, but I didn't find the answer up there, so I caught it. But you wind up with 108 over 104 for your time, and simplifies down to 27/26. In 15, we've got a basically it's like a hyperbolic shape in the first quadrant. And we've got these points where we're trying to figure out where the nearest to this point 2 comma 0 is. Again, we write a Pythagorean sort of identity for the distance from 2, 0 up to any point. They are the coordinates, so we're going to take that x and subtract the 2. That gives us this distance here. Then the y distance is simply radical 18 over x. Take the derivative carefully. You wind up with an algebraic statement that we wind up with a cubic. At this stage, I just quickly subbed in the x values, and 3 is the only one that works. So it is 3 comma radical 6 that gives you the minimum. In number 16, we simply take the derivative, and then we can plug in 0, and we can see if that's positive. And it is, and if it's positive, that means it's increasing. So that's sort of a simple example of our derivative test. In 17 here, we've got a cube whose x is shrinking. The surface area is going to be 6 times x squared. This is a related rates type problem, so when I take the derivative with respect to time on both sides, I get the change in the surface area with respect to time is, when I bring the 2 out, 12x, and then whatever dx dt is. We're told that the changing rate is 6 times the rate of change of the edge, so I substitute in 6 times dx dt, and then I just simply solve for x, and I get 1/2. In 18, we've just got a and b, but we know that the product of the two is greater than 0, so that means they're either both positive, or conversely they could both be negative. So I know there must be at least one horizontal tangent, because if you think about it, this again is right-hand, left-hand behavior, both opening up, so there's bound to be at least one point at which the derivative is 0. So it can't be a, and then it's going to be possibly concave up or concave down based on the a and the b values. So we can't say which one of those are, because it could be negative or it could be positive, but we definitely know that the curve has no inflection points, because when we take the second derivative, it's impossible to solve it if they both are positive or both are negative. So second derivative right there tells you that the curve has no inflection points. Okay, and then the equilateral triangle problem, pretty tough to set it up. What you basically have to do is draw a nice sketch and realize that when you cut it down the middle and you're trying to find the area of this shaded part on the inside, that it's all based on our shortcut for the 30, 60, 90 triangle. You should know that shortcut. When you write the equation, half of this is 30, and then you're going to take away this little bit here, which if this is x, this is radical 3 times x. And then this height here is going to be 30 times radical 3, but then take away 2x at the top. Again, if we do a 30, 60, 90 triangle, it's twice what x is, 2x plus x, so that's minus 3x, and then the height when you fold it up is x. So that's the volume. Take the derivative carefully. When you get that derivative, you wind up with a quadratic. It might look ugly, but when you sub it in, lots of things cancel out, and you work it all the way down to 10 radical 3 over 3. That is probably way harder than anything you'll see in the test, but good to practice sometimes. Alright, there you go. Good luck.